And I've started the presentation as well. Please confirm that you can see the presentation. Hello?
Yes, sir. We can see.
Fine. So I request all of you to mute your mics. Um, I'd like to make a point regarding a mistake that I made in the last class. Is that the class, all our lecture sessions are supposed to run for 75 minutes. But by mistake in the last class, I ended in an hour. So today, for instance, we have to start at 8:30 and go on till 9:45. So by mistake, I finished or ended the session 15 minutes earlier. So I regret that mistake, and please bear with me. I will take 5 minutes extra in 3 classes starting today to compensate for those lost 15 minutes. So today, the class is officially supposed to end at 9:45. I'll take 5 minutes extra. Please bear with me. I regret that because of my mistake, this has to be done. Anyway, so let us return to the discussion. I'm sorry, just another point. Just keep a watch on the red recording tab because sometimes Google has some issues. So if you don't see the red recording tab, you inform me immediately verbally by interrupting the class. And also, if you have any technical questions, you keep adding them in the chat so that by the end of the class, I will get a list of the questions and I'll try to answer those questions then and there. So don't wait till the end of the class to write your questions. You keep putting them in the chat, your questions, if you have any. If it's a technical matter, better to discuss it at the end of the class. And if it's a non-technical matter like audibility or visibility or any such issue or loss of recording, you inform me verbally immediately. Okay, so let's return to the main thread of our discussion, which I started in the last class on Wednesday, the first lecture session. So we were to study electricity and magnetism, and this is physical phenomena. These are physical phenomena of the natural universe, and as such, in nature, there must exist something in material form, something that you can hold in your hand, something that you can trap and measure. And that something will give rise to these two separate phenomena of electricity and magnetism, two seemingly separate phenomena of electricity and magnetism. I'm just reviewing certain points from the last class. It was thought that these two separate phenomena were owed to two separate physical elements. In the case of electricity, it was the charge, electric charge, and in the case of magnetism, it was the North Pole and the South Pole. However, later knowledge informs us that there is no such thing in reality as the North Pole or South Pole. It is a convenient representation, and occasionally we shall talk about the North Pole and South Pole. It's not that it's completely useless an idea, but it's still just that, an idea. There is no existence of the North Pole or South Pole in nature. All that exists are charges for both electricity and magnetism. Static charges, charges that are not moving, will give rise to electricity, but no magnetism. But if the charge is moving, it will continue to give rise to electricity, but in addition, it will bring in magnetism. Okay, so that was the point I was driving at with reference to various mechanical contexts as well. And on this particular point, what is a charge? I said that you know, I mean, you know that there is something that exists that you call a charge, but it is very difficult to put a word on it. At the end of the class, somebody asked me a question as to, I mean, on this point, and I gave a recognizable example, that of air. What is air? I mean, you know that you can't see air, but that doesn't mean air does not exist. You feel air. If you stand out, you will feel a nice cool breeze, or you'll feel a strong breeze. You know that there's something that's invisible to your eye, but it's still there, it's blowing, but you can't put any word to it. What is air? Well, not at least more than 300 or 400 years ago. It's some, I mean, like about 300 years ago, Antoine Lavoisier, the father of modern chemistry, discovered oxygen, and he realized that air is composed of various kinds of gases, oxygen being one of them. And then later discovery said that air is also made of another large amount of gas known as nitrogen and trace gases. So, but then, I mean, these are not very easy things to say. I mean, 500 years ago, nobody, even the great Newton, would not have been able to say that. So these are matters of important discoveries. So, I mean, now if somebody were to ask you what is air, they'll say, well, it's a gas that is composed of 80% nitrogen and nearly 80% nitrogen and nearly 20% oxygen, nearly, and whatever remains, a very small bit of other stuff like carbon dioxide and the noble gases and helium, not so much helium, etc., the noble gases and all those things. So, as you can see, so it is with charge. Charges exist. You can't, of course, see an electron with your eye, but just like you can't see air with your eye, but you feel the presence of air, it is breezing across your face, probably right at the very moment. And so it is that you can feel the existence of a charge. Just touch a live wire and you'll know that charges do exist. But what is a charge? You can't put a word to it. You'll say that, okay, a charge is something that carries, well, I mean, a charge. I mean, it's something that carries 1 coulomb or whatever. So there are no real words to it. Okay, so knowing that charges exist, even if we can't put word to the description of a charge, let us look at certain experimental properties of charges. First of all, and these are points I mentioned in the last class, I'll now return to them in greater detail, that there are 2 types of charges. Again, there is no reason, no philosophical or mathematical reason why there should be only 2 types of charges. There could be 100 types of charges or 77 types of charges, whatever. But it so happens that in nature, once again I stress, we are not doing mathematics, we are not doing philosophy. Ultimately, we may use mathematics, but that is just as a tool to convey facts of nature or describe facts of nature. But ultimately, in our study of physics, nature is supreme. We have to go back to her and get facts out of her. And what are the facts? That there are only 2 types of charges. That is an experimental fact. And so we say, I mean, we could have given the 2 types of charges all sorts of names, 0 and 1 probably in a binary sense, whatever, but it so happened that by convention, they were called positive charges and negative charges. So this definition is also by convention. Its definition was set by Benjamin Franklin. Incidentally, because of him, that we have this little conceptual difficulty of what is a current. Little conceptual difficulty, but we have adjusted our minds to that, or psyche to that. What is it? We say that current is the flow of positive charges. That is by definition. But in reality, what happens that in a good conductor, let us say copper, in a good conductor, what actually flows are not positive charges, but negative charges, electrons. There are free electrons in copper, and it's that it's these things that flow. So we say, but the reality is in nature is that negative charges flow in a good conductor, electrons that is, but by then the definition of positive and negative charges had been established. Hello, somebody please mute the mic, don't cause a distraction. So in reality, it's negative charges that flow, but that was once again a later discovery. So then what do you do? If the convention had been set, nobody wanted to overturn history. So you say that, okay, I mean, it's in reality, electrons flow. We just say that the flow of negative charges in one direction is the equivalent of the flow of positive charges in the opposite direction. And therefore, that's how we now understand currents to be. Or as I said again, it's more a matter of our convention and definition. In reality, what flows are negative charges. So there are 2 types of charges in nature. Okay, and next thing is that, so that is the first experimental fact. So we are just going through these experimental facts. Charges of the same type seem to force one another away. So they repel. You have 2 positive charges, they will repel one another. You have 2 negative charges, they will repel one another. You have one positive charge and one negative charge, charges of opposite type, they will attract each other. So that's another experimental fact. So first we shall have to gather together all the experimental facts that we can get from nature, and then we shall build our theory from there. Okay. Then the third point, charges occur in discrete amounts. What do I mean by that? Well, if you go down to nature, you will see that basically what a minimum irreducible amount of charge is the charge of either a proton or an electron. Although I'm getting ahead of the story, because these are not very easy things to understand or discover, by the way. Be respectful to the people who came across these discoveries. It's not so very easy. I mean, if you were not to have known that there was the existence of charges and stuff like that, and I say then I'll go and see whether charges are continuous or discrete, how would you do it? It has taken a lot of ingenuity to come up with these facts. So they are not very easy. Just like if you just look out at your ceiling, you will say that I can only see the ceiling and probably the ceiling fan and everything. But do you realize that between you and your ceiling, there's a whole lot of air trapped, a whole lot of nitrogen and oxygen molecules buzzing around? You wouldn't even imagine that those things are there, but they are there. So the discovery of these things, casually, however much we talk about these things now, they were not very easy discoveries to make. And so it is that how would you know a charge? I mean, an electron, a proton, or all these things, they're so you don't even, nature hasn't designed you to think of these things. Let me put it that way simply. Nature has not designed you to think of these things or even realize that these things exist. And yet you do. And so it is that you come across this discovery that charges occur in discrete amounts, an integral multiple of a minimum irreducible amount. And what is that minimum irreducible amount? Either the charge of a proton, which comes with a plus sign, as here, I hope you can see the movement of the cursor on the screen, or an electron, as in the minus sign over here, where n is an integer. So you have these numbers, e minus 2 plus 11, 101, but you will not get 2.712 or 1.414 or 3.1412, whatever it is, 3.1415926, that's pi. Yeah, so you will not see charges come up in these amounts. However, when you talk about a current, you know that what actually is flowing is a granular flow of electrons. Granular meaning one electron, a little bit of empty space, another electron, like grains, right? But you can approximate at times this granular flow as a continuum, meaning that as if there is no gap between. I mean, it is like the smooth distribution of a jelly or jam or butter that you apply on your bread to eat. So it's something like that. You do the same thing with, let's say, water. You have a glass full of water, you look at water. The reality of water deep down is that it's made up of H2O molecules. So you have a whole bunch of H2O molecules with empty space among them, right? But that's not how you see water. What you see is a liquid continuum. It's a continuous distribution of liquids. So to your eyes, current flow is also like that. It's a continuous flow of positive charges, like a continuous jelly or a continuous water flow. Incidentally, in the context of water, I hope you realize that the word current is also used. You say that the Himalayan rivers have a very strong current, right? Current meaning a continuous flow of something. So that's how you see it. So charges occur in discrete amount. In the last class, by the way, I gave you the example of sand. I remember. So it all is a matter of perspective on what scale you see something. If you look at sand, dunes of sand moving in a desert in a strong wind, it'll look like to you that it's a continuum wave of sand going one crest after the other. But if you look at a fistful of sand up close, you'll realize that sand is composed of very small grains. And so it is with H2O molecules in water, and so it is with electrons or an equivalent amount of positive charges in a current, except that sand grains can be seen with your eyes without the necessity of a microscope or whatever, or any optical device, but you can't see electrons or H2O molecules so easily. Not even under the microscope would you be able to see those things. Okay, now comes something important. So we touched upon these things in the last class. Today I discussed them in greater detail. Now let us come to another point. This is a particularly important point, and you'll need this point again and again, or refer to this point. Particularly in the last class, somebody did raise the question of Maxwell's correction to one of the so-called Maxwell equations. So this idea that I'm talking about will be useful later in that context. So what have I written over here? Let's see. Charges of opposite signs are in exact balance, both underlined globally and, very importantly, double underlined and in uppercase, capital letters, locally. Let us now try to understand this thing. Charges of opposite signs are in exact balance, both globally and locally. I have given you, let us say, a wire of copper. Try to understand this physical discussion carefully. I have given you a wire of copper. Of course, you know that copper is a good conductor, but right at this moment, the wire that you're holding in your hand is not connected to any battery or anything, so there is no current flowing through it. But your advanced knowledge of physics will tell you that the wire is made up of copper atoms. Of course, everything is made up of atoms after all, atoms, molecules, and everything. And what are atoms made of? Atoms are made of a positively charged nucleus where protons reside, protons being positively charged particles, whereas in the outer part of the atom, you will have electrons. Okay, fine. So you'll have protons and you'll have electrons. Atoms are, after all, made up of charged particles, separate charged particles. Okay, fine. So that's there. But when you touch the atom, when you touch the copper wire, you don't feel a shock. Why don't you feel a shock? Because the number of positive charges in that copper wire, remember, the copper wire is made up of atoms, and atoms are made up of positive charges and negative charges, protons and electrons. Protons sitting at the center at the nucleus and electrons all around. That's a convenient representation of the atom, but it's not a completely correct representation. But I shall not go into that part also, not now. So you don't feel a shock if you touch just a harmless copper wire lying on your table or workshop, wherever. You pick it up casually. You don't feel anything. Why don't you feel anything? Because overall it's charge neutral. Why is it charge neutral overall? Because the total number of positive charges in that is exactly balanced by the total number of negative charges in that. So globally, all through the wire, you will have an exact balance of positive and negative charges. Now, why am I saying using the word globally? Globally meaning all over. For instance, when you say the pandemic is a global problem, meaning that all over the world it is a problem. It's not just a problem confined now to India or America or China or Europe, whatever. No, globally it is a problem. Everywhere it's a problem. So the pandemic is a global problem. So it's there everywhere. So it is that. Here, when you use the word globally, you mean all over the copper wire. So globally, the charges are balanced. But is it possible, now you follow this point carefully, is it possible, in fact, it is possible, theoretically it is, I say that globally, the total number of positive charges will equal the total number of negative charges. Fine, that's all right. But that does not exclude the possibility that all the positive charges will be bunched up at one end of the wire and all the negative charges at the other end of the wire. Even then, overall, the total number of positive and negative charges will be the same inside the wire, except that all the positive charges are gathered at one end of the wire and all the negative charges are gathered at the other end of the wire. So global charge balance is there, but now let's look at the second word, locally. But are the charges balanced locally as well? What do I mean by locally? You break the wire down the middle. Suppose your charges, let's consider this hypothetical scenario. Your charges are gathered, all positive charges at one end and all negative charges at the other. And somewhere down the middle of the wire, you have broken it. So then now you will have the scenario that you will have two pieces of wire. One piece will contain only positive charge and the other piece will contain only negative charge. But does it really happen? If you use a wire cutter and you snap the wire in the middle, and then you hold the two pieces separately, do you feel a shock? No, you don't. If the charges were to have been gathered at the two ends, positive charges on the one side and negative charges on the other, then if you were to have cut the wire down the middle and then held one end, you would have felt a shock, because then there would have been an excess of charges at that end, one kind of charges at that end, and those charges would want to seek an outlet. Because let's say you have a whole bunch of positive charges at one end. The positive charges are going to repel one another, right? They want to move as far as possible away from one another, but they are not getting any outlet. As soon as you touch with your finger, they will get the outlet that they were looking and travel through your finger. That's how you will feel the shock. But you don't feel any such shock. What does it mean then? That within the wire, of course, there is a global balance of charges, but there is also a local balance of charges. You can take any small bit of the wire, break any small bit of the wire out, and in that small bit of that wire, howsoever small it might be, the total number of positive and negative charges will continue to balance each other out. Look at the Earth. We say that the Earth, I mean, you know, in electricity problems, you say that let us earth this device. Or even in your household appliances, like let us say a lightning conductor, you say that we have earthed this device or this thing, whatever. What do you mean by earthing something? We are a part of the Earth. The Earth globally is a charge-neutral planet. The Earth doesn't have an excess of either positive or negative charges. But then, locally also, the charges are balanced out all throughout the Earth. It is not that all the positive charges are gathered in the northern hemisphere and all the negative charges are gathered in the southern hemisphere. You pick up a small amount of earth matter, a lump of clay or a stone or whatever from the ground. Incidentally, you're also earth matter. You're made up of things that are there on the earth, every one of us. What are we made of? Carbon, nitrogen, oxygen in the amino acids, glucose, so that's also carbon, hydrogen, oxygen, sugars, basically iron in the blood, all sorts of things. So we are all made of earth matter. And unless otherwise tampered with, everything that exists on the planet Earth is a charge-neutral object globally. Meaning that if I were to touch you or anything in your room, you were to touch it, you will not feel a shock. Everything in your you see around is charge-neutral. Why? Because it is because of this property. The charges of opposite signs are in exact balance both globally and locally. So the Earth is an overall charge-neutral object both globally and locally. So as if you have an excess of current bunched up somewhere, as in happens during a lightning strike. What is lightning strike after all? Lightning strike is a very simple thing, because incidentally, let me just have a little discussion of that. What happens is that, why does a lightning strike happen? Clouds gather, they cause friction among themselves, they get charged, right? So there's a charge build up somewhere. But charges, the natural tendency of charges is to move out. Charges of the same type, natural tendency they have is to move away from one another. So they are now trying to move out from one another, but they can't because there is no passageway. But if there is a massive buildup of charges, then why don't they have a passageway? Because the only passageway they have is through the air, and the air is an insulator, right? So the only passageway that they can have is when they have a large buildup of charges is to break down the air insulation and come from the top down to the earth as a bolt of lightning. That is a lightning strike. So you can see lightning strike is happening because of two things. A large buildup of some charges up in a cloud. These charges are trying to move away from one another, but they can't. Why can't they? Because there is no easy way out. But eventually they have no choice. Desperately they are trying to break out. So much so that they will even break down the air insulation and come down from the clouds as a bolt of lightning to the earth. And why will they come down to, why would they tend to come down to the Earth? Because there's charges of opposite type down there on the Earth. So they will come down and balance one another out. So so this tendency for local balance and this, what is it? Opposite charge, sorry, like charges repelling basically are the root cause of a lightning strike. Okay, so I hope you have understood the exact balance of global and local balance. These are important. This is an important physical idea which we shall use later in various a large amount of, I mean, a whole lot of mathematical discussion later. Ultimately, we shall gather the physical facts and put them together to frame a mathematical theory. Okay. Now, let us look at something else about charges. A single charge in isolation cannot be created or destroyed. This is known as the law of conservation of charges. Right. Can be neutralized. I use the word annihilated. Annihilated meaning destroyed, but I shouldn't use the word destroyed, so I corrected that, although I'm keeping the word annihilated. But a single charge in isolation can be neutralized with an opposite charge of opposite sign, right? So, for instance, an atom, you've got a positive charge, okay, at the center. The electron cloud all around will neutralize the positivity of the central nucleus, and in the process, it will also get neutralized itself due to the its own negativity will get neutralized due to the positivity of the nucleus, and overall the atom will appear charge neutral. That's why you use the word neutralized over here. But a charge that is there in isolation cannot be created or destroyed. It's just like your standard conservation rules. In conservation rules, what do you say? Matter is neither created nor destroyed. Energy is neither created nor destroyed. Incidentally, that was before Einstein. Matter can neither be created nor destroyed. This thing was the discovery of Lavoisier, whose work I mentioned, whose discovery of oxygen I mentioned just a while ago. What he found was that in a chemical reaction, all that you start with still remains all that you start with before a reaction still remains the same. I mean, you still have the same amount of matter at the end of the reaction. For instance, just consider a simple reaction. You have sodium hydroxide, which is a base, and you have hydrochloric acid, which is HCl, which is an acid. So base is Na, sodium hydroxide is NaOH, and hydrochloric acid is HCl. So when you make the two things react with each other, so this is what you start with. You have Na, you have Cl, sorry, you have Na, you have O, you have H, and then you have another H, and you have a Cl. At the end of the reaction, what do you get? You have got NaCl, sodium chloride, common salt. And you've got water, H2O. So 2 hydrogen you started with, 2 hydrogen you still have. So those things are there. So these are chemical reactions, right? So in chemical reactions, what you start with is what you still have at the end of the reaction. And you weigh the amount and you find that is the same. That was the great discovery of Lavoisier. But of course, Lavoisier's main discovery was with water and I think something else. I mean, he carried out the experiment and he found that he started, I think he split water. Sorry, yes, I think he split water. He split water into hydrogen and oxygen. That's what he did. And he discovered that there's this gas called oxygen, which is also there in the atmosphere. He could breathe that and you feel better. That's why patients, when they have respiratory difficulties or they feel unwell, they are given oxygen support. So yes, so that was, so whatever you start with before and after, whatever you start with before a reaction, you still have the same thing after a reaction. That's the law of conservation of matter. And similarly, thermodynamics, the engineers who worked with thermodynamics set down the laws of thermodynamics. The first law of thermodynamics says that energy is a conserved quantity. And so matter and energy are conserved quantities, which was understood, but then later Einstein showed that, well, matter can be convert it to energy, and as a result, you have a little bit of mass loss. And energy can be created out of matter, and vice versa also. Those things are possible. So he gave it through his famous formula, E is equal to mc squared, energy matter equivalence, energy mass equivalence. But for that, that's not a very easy thing to discover. That's not a very easy thing to prove from nature. Lavoisier could not show that through his chemical experiments. In chemical experiments, you will not be able to see this thing very easily. But if you, sorry, in chemical reaction, you will not be able to see this thing. But if you carry out a nuclear reaction, then very much it is possible for you to see this property of nature, that matter can be converted to energy. Not in a chemical reaction. What do I mean by not in a chemical reaction? And you just take water and split it into hydrogen and oxygen, or you just take sodium hydroxide and HCl. These are very simple chemical reactions. You will not see energy mass equivalence in these things. But if you shoot a neutron hitting a uranium-235 nucleus is not a chemical reaction, but it is a nuclear reaction. A neutron is not a chemical not a part of your laboratory chemist's stuff. A neutron is breaking down the nucleus to bring something out, a neutron that is. And you shoot that neutron into a uranium-235 nucleus and you'll get your atom bomb. If you have a sufficient amount of U-235 nuclei, that is. So there you will convert matter to energy. So you can see, I mean, although we say that these things can neither be created nor destroyed, well, matter can be destroyed to create energy and vice versa. So Einstein's physics says that matter and energy together can neither be created nor destroyed, or rather matter and energy together make a conserved composite. But let's come back to charges. A single charge in isolation is can neither be created nor can it be destroyed. But you can isolate charges. That is a very important point, right? But you cannot. I've written something down over here. Magnetic poles. Let us go back to our idea of a north pole and a south pole. Let us go back to that idea of a north pole and a south pole. And let's refer to your commonplace experience. Maybe, can you just bear with me? I'll stop this presentation and refer to another presentation, and then I'll come back to this thing. Right. Just bear with me, because I've got a supplementary set of notes where these things are discussed. Maybe I'll just stop this presentation for a few minutes. I'm restarting the presentation with a new set of notes. Please just confirm that you can see that. Can you please confirm? Wait a minute. Can you see this thing, please? Hello?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So here it is that energy conservation, as I said, I mean, I just touched upon it. Okay. Please mute your mic. Please mute your mic. So energy conservation, energy is neither created nor destroyed. That's all very good. Matter conservation, total amount of matter before and after an interaction. That is example, a chemical reaction is the same. And but Einstein comes later. Einstein came after the thermodynamics people and Lavoisier, and he showed through his energy mass equivalence formula that energy and matter are interchangeable, but globally meaning overall, energy and matter obey a conservation rule. So that was now let's in the previous set of notes, to which I shall go back shortly, I talked about isolation of charges. Now, what do I mean by isolation of charges? By isolation of charges, I mean that let's consider an atom. For the time being, let's consider an atom. You can isolate the negative electron from an atom, pull away the negative electron from an atom, and as a result, what are you left with? A separated electron and the central positive charge, the central positively charged nucleus, by which now you say that the atom has become an ion, I-O-N. a positively charged ion. So that is very much possible. You can take an atom, you can break it, you have a positive charge at one end and a negative charge. And it's not a very difficult thing to break an atom in that sense. You could do it in these batteries where you have anodes and cathodes. These were all done more than 150 years ago. It did not need a huge amount of technology. You put a little salt water or something, and you will see that it will be split into positively charged ions at the one end and negatively charged electrons at the other end. So the positive charges will go towards the cathode and the negative charges will go towards the anode. I think I'm making a correct statement, I hope. Yeah. And so you will have cations and you'll have anions and all those things. So you can separate charges from one another. That is to say, you can have isolated charge. What is the physical element of electricity? A charge. What is the physical element of magnetism? Let us go to the old historical idea of North Pole and South Pole. For the time being, let us forget my old statement that there is no such thing as a North Pole or a South Pole. So we are living in the times before that discovery. So what is the physical element of magnetism? A North Pole and a South Pole. Okay, just like charges, electricity comes from a positive charge and a negative charge. There is a symmetric carryover of that idea to magnetism, and you say that magnetism is due to a North Pole and a South Pole. Okay, so here it is your magnet. You have a bar magnet with a North Pole and a South Pole. Okay. The magnetic field lines are coming out of the North Pole, and then they reconnect with the magnet through the South Pole. Likewise, over here, the North Pole, the field lines are coming out of the North Pole. That's the arrowhead direction going into the South Pole. Very good. Now, just like you can isolate charges, you say that I am able to isolate a charge, a positive charge from a negative charge. And that's what we do in this anode-cathode business. So can we then isolate a North Pole from a South Pole? Very surprisingly, no. How not? Or why not? Let's see. Well, first, how not? Why not is a very difficult question, actually. We'll address that why not later. I mean, how do I isolate the North Pole from the South Pole? Very simple. You break the magnet down the middle. Here is the magnet. You break it. It's an intact magnet. You break it down here. So here it is. You break the magnet down the middle. And to your great surprise, what you discover is that you would have thought that just like if you break an atom, in your left hand you'd be holding the positive charges, and in your right hand you'd be holding the negative charges, and they are well separated from each other. So you have isolated charges. So you would expect that now you would isolate North Pole from South Pole. Very strangely, as soon as you break a magnet, down here, from the point where you have broken, just a little above the point of breakage, a new South Pole will be born, and just a little below the point of breakage, a new North Pole will be born, and the top broken piece will behave like it's an isolated magnet in its own right, with its own set of the previous North Pole and a newly born South Pole. So that is what is written over here. As soon as a bar magnet is broken, a new North Pole and a new South Pole are born. So a new North Pole in this bottom part and a new South Pole, or rather a new North Pole in the top part of the bottom half, and a new South Pole in the bottom part of the top half. So they are born now. Okay. So basically, then the field lines will again spill out of the North Pole and close upon the South Pole here. And field lines would appear to come out of the newly created North Pole and reconnect with the old South Pole. So you will just end up having two new magnets, each with its own North and South Pole. So you can continue breaking the magnet down to whatever small piece you want to. This thing will keep replicating itself. Moral of the story is that a magnetic monopole. What do I mean by a monopole? A monopole, mono meaning single, pole meaning north, south, whatever. You can have an electric monopole in that sense. A positive charge is an electric mono charge or monopole if you like. But you can have isolated electric charges, but you cannot have isolated magnetic poles. An isolated pole does not occur. They do not exist. Well, for that matter, north and south poles also do not exist, but that's something that I shall touch upon later. We shall come back to later. But the fact is that uh, magnetic monopoles do not exist in nature. And this is a very important point, really. And I think I've got something else over here. Yeah, and I just would like to mention something. Global and local balance of charges. Global and local balance of charges. Here we are talking about. I just like to touch upon something. I've talked about this global and local balance of charges. Charges are globally, so here's this diagram. Here in this thing, charges are globally balanced. What do I mean by charges are globally balanced? You just see 1, 2, 3, 4, 5, 6 columns of double rowed positive charges, and similarly 6 columns of double rowed negative charges. So the total number of positive and negative charges are the same. Globally they are balanced, but not locally. But here in this diagram, they are homogeneously mixed. So charges are balanced both globally as well as locally, meaning that you have a homogeneous mixture of charges both globally and locally. This is like a khichdi of charges. All the dal and chawal are homogeneously mixed. But this is like biryani. I don't know whether you know what biryani looks like, proper biryani, not this masala rice stuff that you get in the DICT mess. Oh, well, then you have not experienced DICT mess or anywhere that is. Proper biryani, if you go to Lucknow and see how biryani is prepared, these are the famous biryani places, Lucknow, Hyderabad. I've been to Lucknow, and also so there in biryani what you have is that you have various kinds of rice placed one top of another, and when the cooking gets done, the various layers of rice don't get mixed, so you will have various layers in isolation. So overall there will be a balance of because biryani requires a balance of two different kinds of rice, plain white rice as well as saffron rice, right? You don't want to have excess of the one over the other. But when the biryani is cooked, these different kinds of rice are kept in separate, get cooked in separate layers. When it is served, they are mixed. But while it is cooked, they remain isolated from each other. So this is like khichdi and this is like biryani. So that is what you have. Okay, there's one last point I'd like to touch upon regarding this local and global balance of charges. It's just that of course, the latter distribution is natural. Why, incidentally, do you think that the latter distribution is natural? It's a very simple argument. You can give the answer right away. The answer is that this whole bunch of positive charges and this whole bunch of negative charges within this pack, they'd want to get away from one another. And within this pack, they'd want to get away from one another. And they will be attracted, negative charges will be attracted towards positive charges and vice versa. So as a result, they'd want to get away from their own kind and get mixed up with charges of the other kind. So that's why this local balancing is a very natural tendency. However, it doesn't keep going on down to any scale of matter you want. Ultimately, when you go down to the scale of the atom, be it understood very clearly, in an atom, the positive and the negative charges are no longer locally balanced. What do I mean by no longer locally balanced? The positive charge at the center, let's say the nucleus at the center, is very much far away from the negatively charged electron cloud. The nucleus is a very small sized object of the order of 10 raised to minus 15 meter, 10 raised to minus 15 meter. That's the typical size of a nucleus, whereas the overall size of an atom is 10 raised to minus 10 meter. So you can see a nucleus is about 1 lakh times smaller than the rest of the atom, and the electrons are there outside on the rest of the atom. So on the atomic scale, positive and negative charges are distinctly separated. So this local balance thing can only go so far and no more. They can't go down to any scale you want, and you'll continue to have this balancing on the scale of the atom. They are, of course, distinctly separated. Incidentally, one point I'd like to touch upon is that youth would think that, see, the mass of an electron is very much less than the mass of a proton. An electron has got a mass of 9.1 into 10 raised to minus 31 kg. A proton is 1800, nearly 2000 times heavier than that, more massive than that. That's the mass of a proton. So you would think that since protons have larger mass, protons will also take up larger volume, larger space. And since electrons have smaller mass, electrons will take up smaller amount of space. That is going by your commonplace experience. A smaller object takes up, if you look at your table or your mobile phone has got a lot less mass than, let us say, your fridge. As a result, your fridge takes up a lot of space and your mobile phone does not take up too much space. Why? Because mobile phone has less mass. Unfortunately, that is not the thing that happens on the atomic scale. The proton, which is much more massive than the electron, is confined to the nucleus, whose size is 10 raised to minus 15 meter. And the electron, which is much less massive than the proton, is distributed on a length scale of 10 raised to minus 10 meter. 1 lakh times more space it takes, or along one length dimension, it's 1 lakh times larger than a proton. How surprising that is. But that is, again, a surprising fact of nature on the atomic scale. On the atomic scale, surprising things happen, which is the reality. Once again, I keep saying to you, go to nature, look for the reality. Sometimes you may not be able to put words to that reality. You can't put word to what a charge is. 500 years ago, nobody would have been able to put words to what air was, right? And so it is that for the atom, nature has not designed you to see atoms or realize atoms. That's why you can't put words to atoms. How do they behave? They may seem surprising from your scale of experiencing nature, but nature's own scale or nature's own operational principle does not have to respect the way you see the world. Anyway, so let me now go back to the old thread of our discussion. I'll stop the sharing of this thing. I hope you have understood this point that I was trying to make. I shall now touch upon the inverse square law force. And for that, there is a little bit of discussion that I have had. I'll just touch upon this thing, inverse square law force. See, you know of two inverse square law forces, one in gravitation, one in electrostatics. In gravitation, you have Newton's inverse square law force, F is equal to minus G m1 m2 by r squared r cap. That's the full formula of it. We'll discuss this formula later. And Coulomb's force is F is equal to Q1 Q2 by 4 pi epsilon naught r squared r cap. So there is a very important similarity between these two forces. Both are 1 upon r squared kind of force. However, I'm just discussing this point. However, gravitation is always attractive. Why is gravitation always attractive? Because of this minus sign. As soon as you put a negative sign before a force, you'll get an attraction. All right, its tendency to go towards a certain preferred center. And electrostatics is repulsive if charges are of the same sign, meaning Q1 and Q2. You just see if Q1 and Q2 have the same sign, both plus, overall positive sign, both minus, again overall positive sign, minus into minus will be plus, right? But if they are of the opposite sign, then plus into minus will give you a negative sign overall. So basically, in the case of gravity, you have to force this minus sign. But in the case of electrostatics, the overall outcome of either a plus sign or minus sign will be taken care of by the charges themselves. So try to understand these 2 points, that the similarity between, in the last class, I talked so much about forces, and you were wondering why was I fussing about mechanics and forces. Mechanics is not very far from electromagnetic theory in various ways, and you will see how. So that's why it's also useful to occasionally refer to mechanics, and gravitation is a very standard example. I'll be talking about gravitation a lot in the context of electrostatics. You'll be surprised, you may be surprised, but don't be. because of this great similarity of 1 upon r squared. Now, why should I be talking about gravitation? Because gravity is something that you can always feel all the time. Just at this very moment, if you drop an object that you hold in your hand, you will see gravity in operation. See, for the very fact that you are sitting in your chair is proof that gravity is unavoidable, inescapable. You can't escape gravity. But you can't see charges. But knowing that 1 upon r squared is a very important similar property between the two of them, we can occasionally refer to gravity by an analogy to understand the behavior of charges in the electrostatic context. That's why make a note of this fact that in gravity, this great similarity between, between gravity and electrostatics, there is this one great similarity of 1 upon r squared. But there is a great difference. Gravity is always attractive. Why is it always attractive? Because masses are always positive. There is no such thing as a positive or a negative mass. So since masses are always positive, overall their product will always be positive. And that's why to ensure that you are getting the attraction, you'll have to put a minus sign. Negative force means attraction. It was due to Newton. This r cap and r squared business, all those things I'll discuss later when I start discussing vectors, not now. But in the case of electrostatic, the force may be attractive, may be repulsive. You don't know. It will depend on the respective signs of charges. Anyway, so with those 2 points, 1 upon r squared and positivity and negativity, or rather attraction and attraction here all the time, and here attraction or repulsion, we don't know beforehand. We will go back to the old presentation now. So I'm stopping this sharing. If you don't be too confused by this, I hope you're not getting too confused by this back and forth movement. So I will just go back to reopening the old presentation, and I will request you to confirm that you can see the presentation. Can you see the presentation? Hello?
Yes, sir.
Yes, sir.
Yes. Okay. Thank you. Okay. So as I said, in the supplementary set of notes, I touched upon this. I showed you a description, diagrammatic representation of global and local balance of charges. I talked about your ability to isolate a charge, which by itself can neither be created nor destroyed. But then I raised this question, can you isolate magnetic poles? I gave you a diagrammatic representation of why you cannot isolate, or how you are not able to isolate magnetic poles. Why you cannot is a very difficult question. As I said, we'll come to that question later. So you cannot isolate magnetic poles. And now we shall go to that last point which I talked about in the last, that supplementary set of notes, Coulomb's law and gravity. Coulomb's law as in electrostatic force, Fe, F subscript E as in electrostatics, and gravity as in the case of Newton. Now, scale of interaction of forces between two charges. Let us begin a long discussion on this thing, detailed discussion of this thing. We have got two electrons. The fact is that electrons have negative charges. Okay, that's very good. And what is the value of that negative charge? Minus 1.6 into 10 raised to minus 19 Coulomb. In the SI system of unit, there are other systems of unit which will give you other values, but in our course, we shall stick to the SI system of unit. Okay, fine. So Coulomb's law says that if you have got two electrons, then they will be repelling themselves. That is the point here. So you have got two electrons. Just this point that I was touching upon a while ago, Q1, Q2 by 4 pi epsilon naught into 1 upon r squared is the electrostatic force due to Coulomb. Very good. And so what are the two charges you're talking about? Q1 and Q2 are two electrons. So E and E, value of E is 1.6 into 10 raised to minus 19. Minus and the minus signs here are telling you that we are talking about two negatively charged particles, namely electrons. So minus and minus will be plus. So overall, you will have Fe, the electrostatic force between two electrons, to be E squared by 4 pi epsilon naught into 1 upon r squared. So the positive sign implies a repulsive force. But, ladies and gentlemen, do not forget something. Nature is not going to come to you isolated in one form or the other. She will come before you in all forms at the same time. What do I mean by that? The electrons also have masses. We are talking about the physical universe. In the last class, I said to you that in the physical universe, you have objects, real things that you can hold in your hand, or you can gather in a box, or you can make measurements of. Okay, fine. So if that be so, and everything in the physical universe comes, I mean, not everything, but many things in the physical universe come with in a material form. What do I mean by not everything? I mean, there are things that do not come in a material form, meaning that they don't have to be like it's something that you can hold in your hand. For instance, you can't hold entropy in your hand, thermodynamics, but I'll not get into that. So I should just qualify my statements. That in the physical universe, many of the things that you'd be interested in come in a material form. Many of the things, but not all of the things, come in a material form. So what do I mean by material form? Something that you can hold in your hand, you can make measurements on, you can put on a weighing machine and find what mass it has. That is to say, electrons, in addition to having charges, will also have masses. Okay, that's fine. So if electrons have charges as well as masses, then you are going to wonder, if two electrons are going to repel one another, each other, because of Coulomb's attraction, Coulomb's law, repulsion in this case, but then having masses, aren't they going to attract each other? So the same thing, the electron has got mass, the electron has got charge. You bring two electrons next to each other. Coulomb's law will say that they are going to repel each other. And Newton's law of universal gravitation will say that they are going to attract each other. Now, who wins? Is there a balance between the two? Or does one dominate over the other? Why do we want to check this thing out? Why? Because we are doing physics. Let us try to see. We can't ignore measurable quantities, if at all they are worth measuring. Make a note of that statement that I have made. We should be interested in measurable quantities pertaining to a phenomenon that we are studying, but only if it is, if at all it is worth measuring. Now, what do I mean by that? Let us now look at the gravitational force between two electrons. What is the gravitation formula? Minus capital G m1 into m2 by r squared, where m1 and m2 are the masses of the two electrons. This minus sign has to be drilled in forcefully because it's a law of universal gravitational attraction. There is no repulsion. We have never heard of gravitational repulsion. So attraction means that you have to put a minus sign, meaning that they will get close to one another, each other. Okay. So this is the gravitational force. Now at a certain distance r, so this is the Coulomb formula, E squared by 4 pi epsilon naught 1 upon r squared. E, epsilon naught are universal constants. 4 pi is a mathematical number. And so it is, if you look at this formula, G me squared, G is a universal gravitational constant, me is the mass of the electron, that is also a universal number. All these things are there. So as per Newton, there will be a gravitational attraction between the two electrons. As per Coulomb, there will be an electrostatic repulsion between the two electrons. Let us now measure the two forces against each other and see which one is important to us. Which one is it? Let's see now. At a particular distance r, let's take a ratio of the two forces, Fe by Fg, G as in gravity, E as in electrostatics. Fe by Fg, and we are taking the absolute value. We are ignoring the sign over here. Let's see, what do we get? E squared by 4 pi epsilon naught, and you'll get divided by G squared. Fe by Fg will give you G by me squared. The minus sign we have ignored. We have taken the absolute value. And you have got the 1 upon r squared here, and you have got the 1 upon r squared here. Both have cancelled, and this is a fixed number. Whatever be the distance r, this ratio will not change. And it's a ratio between two forces. If it's a ratio between two things of the same dimension, then it is a dimensionless number. It's just a pure number that you have to calculate now. What is the value of that number? E by, so you've got E squared by ME squared, E by ME squared, 1 by 4 pi epsilon naught G. Calculate this number. E by ME is 1.76 into 10 raised to 11 coulomb per kg. So charge of an electron is 1.6 into 10 raised to minus 19 coulomb. Mass of an electron is 9.11 into 10 raised to minus 31 kg. When you take the ratio of these two numbers, or these two quantities, not numbers, they have got dimensions and units also. So you'll get 1.76 into 10 raised to 11 coulomb per kg. So that is what you have over here. Capital G, universal gravitational constant, is 6.67 into 10 raised to minus 11. These are all SI units in the SI system of units. So it's per kg cubic meter per second squared. And epsilon naught is got a new unit of its own. Farad per meter, 8.8 into 10 raised to minus 12 farad per meter. What is farad the unit of? Farad is the unit of a capacitor, capacitance. We'll talk about capacitor later, but I'm referring to something, a few things that I'm sure that you would have learned at school. Otherwise, you could not have qualified in the JEE and come to DICT. So in CBSE syllabus, these are all there. And also in all the other syllabi of other boards of India. Anyway, so here you have these numbers. When you have these numbers, Fe by Fg comes out to be, you see this number? Electrostatic force of repulsion is 10 raised to 42 times stronger than the gravitational force of attraction between two electrons. You have got two electrons. Fe by, so Fe is the electrostatic repulsion between the two. Fg is the gravitational attraction between the two. Both have charges and both have masses. And so you say that, okay, if there's gravity, we have to be careful. We can't leave everything out. And why can't we leave everything out? Look at the start of the discussion. Scales of interaction forces between two charges. We'll come to this point. Scales of interaction forces. Scales of interaction forces is a very important thing. Gravity is insignificant, hopelessly defeated between two electrons. You can see this largeness of this number. It's so large that you can't put a word to it. Once again, I say that there are things in nature that you will come across about which you'd be literally speechless. What do I mean by literally speechless? That you will have no word to describe it. What is a charge? Well, you don't have any word to describe it. And similarly, this number 10 raised to 42, you have no word to describe it. The largeness of this number. What is the kind of large numbers that you are acquainted with? Billion, 10 raised to 9, million, 10 raised to 6, trillion, 10 raised to 12. We'll say that, you know, the human population of the world has become very large. How large it is? It's somewhere a little above 7 billion. 700 crores, right? India's population is something like 130 crores. China's population is something like 140 crores. World population is something like a little more than 710 or 20 crores or something like that. So you say 7 billion, right? Okay, fine. So that is all right. So what is a billion? 10 raised to 9. You can put a word to it. You can always say, okay, we can get some sense of the largeness of this number. Trillion is 10 raised to 12. Right now, the size of the global economy is about, overall global economy is about $90 trillion, right? The global GDP. The global GDP every year produced by all the countries, including America, China, all the large economies of Europe, Asia, Japan, India, all these countries put together, and then all the smaller countries, it's $90 trillion, US dollars, that is. So 90 into 10 raised to 12, so 9 into 10 raised to 13. So those are the kind of large numbers that you experience, and you have words to describe those large numbers. You have no word to describe this 10 raised to 42. Just imagine that if the gravitational attraction between two electrons would be 1 Newton, gravitational attraction is 1 Newton, then the electrostatic repulsion between the two of them will be 10 raised to 42 newtons. 10 raised to 42. I mean, how large is that number? I mean, you can, there is no word to describe this number. So gravity is hopelessly defeated in the context of our studies of electrostatics. And hereafter, therefore, see, ultimately we shall be talking about things that will have charges, but charges don't come without a mass. Why so? Because charges are also massive objects. By massive, I mean they're material objects. And as such, they must also have this other quantity known as mass. Otherwise, nothing exists in the material universe. Once again, I'm sorry to have made an incorrect statement. Most things that exist in the material universe must come with a mass. Charges are material objects, right? Once again, I say there can be various things in the universe which are non-material. They can be measured. Temperature. Can you hold temperature in your hand? Can you hold entropy in your hand? Those are all measurable quantities, but they do not have, I mean, you can't say that here am I, you can say, here am I holding up a 5 kilo mass. Okay, but you can't say, here am I holding up 30-degree temperature, something 30-degree temperature. No, you can't, because so there are things that don't come like that in a material form, but charges come in a material form. And if they come in a material form, then they must have a mass. The question is, we are going to discuss electromagnetic theory. We are going to make measurements and observations about things that belong to the domain of electromagnetic theory, but then the physical element of electromagnetism is a charge. Okay, meaning that we'll have to study the properties of charges. But charges also come packaged with a mass, whether you like it or not. So to understand the interaction of charges, should we or should not we also refer to mechanical properties that arise due to the presence of masses? That is to say, refer to the laws of Newton's laws of mechanics. Should we or should we not? Answer is, we should not. Why we should not? Because when we study electrostatics, now comes something here, that statement that are scales of interaction forces between two charges. Example to electrons. Example. I mean, other charges will also can be worked upon, but electron was a very simple example to work on. Scales of interaction forces. Remember forces. What is force? Force is a mechanical property. The person who referred to force for the first time in clearly measurable terms was Newton. And he did so in the context of the laws of mechanics, not in the context of the laws of electromagnetic theory. He did not work under a reading lamp or ceiling bulb or anything. In his time, there was no electricity magnetism. I mean, there was, but people did not know what to make of it. So Newton is to work in candlelight. So he was referring to the laws of mechanics. But forces are very much a part of laws of mechanics. But now we see forces also appear in electromagnetic theory. Step by step, try to understand this thing with full clarity. If I ask you what is a force, don't straight away give the answer mass into acceleration, because in this formula, I cannot see any mass or any acceleration. Not in this formula, sir. This is an electrostatic force, and on the right-hand side, there is no mass or there is no acceleration. Once again, I stress on this fact that nature comes with the same thing in various different forms. One phenomenon of nature blends into another. So don't say that when we are studying electromagnetic theory, mechanics is not to be considered. Is it to be considered or is it not to be considered? Well, it is to be considered, and it is not to be considered, depends upon the circumstances. When is it not to be considered? When we deal with forces of interaction among two charges, we do not have to refer to the forces of interaction that also arise because of their masses. Why not? Because the mechanical properties, by mechanical properties, I mean the properties that arise due to the laws of mechanics, things that have mass, they are there. They are contributing. I'm not denying that they are not that they are contributing. That can't be denied. However, the scale on which mechanics is making a contribution is hopefully drowned by the scale at which electrostatics is making a contribution. If mechanics is contributing 1 unit, electrostatics is contributing 10 raised to 42 unit, as per this very simple example that we have discussed. So when we discuss scales of interaction, or when we discuss forces between charges, forces among charges, we shall be referring to a mechanical property called force. But we shall not be referring to things like mass into acceleration. Why not? It is not that they are not happening. It is not that they are not happening. They are very much happening, but they are happening on a scale that is insignificant. Our primary requirement is to look at things that are happening on a much more forceful scale, much more powerful scale, dominant scale. So 10 raised to 42. So we can ignore now things that come. We will be working with forces. Be it understood very clearly. We'll be talking about Coulomb force and all those things. But we will not be talking about mass into acceleration kind of a thing. We will be talking about this kind of a formula. We shall not be talking about minus g m1 by m2 by r squared kind of a thing. Not, sorry, not when it comes to measurable quantities. What do I mean by not when? Is this force not there? Gravity is making a contribution? Of course it is. But then why are we ignoring it? Because it's not really very important for us. Why is it not important for us? Now we shall discuss this little point in greater detail, scales of interaction forces between two charges. What do I mean by scale of interaction forces? On different scales of nature, different kinds of interaction will happen. I'll give you a very simple example. You are a planetary scientist, let us say. You're studying the solar system. What is the force of interaction running all through the entire solar system, starting with all the innermost planets, let's say Mercury, and then you go Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto. Pluto is no longer a planet, by the way. So what is the scale of interaction? Pluto is so far away from the center of the solar system. Uranus and Neptune are so far away from the center of the solar system. All right, very much. The sun is made up of positive and negative charges. The sun is a hot plasma. What is a plasma? Plasma is a charged gas. The atmosphere of the Earth is not a charged gas. It's a charged neutral gas. But a plasma is a charged gas. So when you study this attraction between, let's say, the sun and a planet like Jupiter, are you not going to then worry about the electrostatic attraction of the charged particles on the sun and the charged particles in Jupiter? Why not? You have the simple answer here. The charged particles will continue to have these values like electrons and protons. They are there. But then, now we will come to something very important. Here, for electrons, we had masses of M1, M2. I'm terribly sorry. Mass of an electron, 1.6 into 10 raised to minus 9. I'm terribly sorry. 9.1 into 10 raised to minus 31 kg. But when you study planets, you're talking about masses like planets and stars. You're talking about masses like 10 raised to 30 kg for the sun, 10 raised to 30. Once again, it's so large you can't put a word to it. The mass of the Earth is 6 into 10 raised to 24 kg. Those are the masses. Those masses will become very large. And therefore, When you want to study the solar system, give me 5 minutes and I'll finish this discussion. Please just give me 5 minutes. We're nearing the end. When you want to study the solar system, you don't have to refer to small things like a bit of charge here on this planet and there in the sun and all that. You just worry about the whole composite mass of that planet. Why? Because then gravity becomes a very important dominant force, much above greater than the electrostatic interaction or the interaction of charges among various celestial objects. But when you want to study two charges, let's say on an atomic scale or whatever, their gravity is no longer a player, no longer a significant player. It is still there. But for two charges, an electron and a proton, or an electron and an electron, whatever, the interaction between them is about 10 raised to 42 times stronger than gravity. So two charges, it is to be understood that you're looking at nature on the atomic scale. Whereas if you want to look at nature on the scale of the solar system, then gravity becomes more important than electrostatics. So scales of interaction forces. On different scales, you will have different kinds of interaction. It is not that the other interactions, I'm sorry, you will have the dominance of different kinds of interaction. It is not that the other interactions are not happening, but they are not very significant. Why are they not significant? Because ultimately you'll be making measurements. I mean, what's the point in making measurement of something like as large as 10 raised to 42 and then adding 1 to it? If electrostatics is 10 raised to 42 units, gravity will be 1 unit. I say that, okay, what's the total force of interaction between two electrons? You are very precisely minded. You will say, sir, the electrostatic repulsion is 10 raised to 42 units. I said, very good. Then you'll say, but the gravitational attraction between the two is 1 unit. So then you'll have to now write 1, and then you'll have to write 41 zeros, and then you'll have to write another 1, and then you'll write unit, a Newton, let's say, whatever. There is no point writing that last 1 after having written 10 raised to 41 zeros. Just 10 raised to 42 will be 1 followed by 42 zeros. So if you want to add 1 to that, you'll have to write 10 raised to, you'll have to write 1, then you'll write 41 zeros, and then you'll have to write 1. Is that last 1 any important? Because ultimately we are not doing mathematical precision. We are doing physics. In physics, we only, in the last class I touched upon this thing, you only go up to what you call least count. You only go up to the things that are significant for you. Suppose I give you a ruler whose least count is 10 raised to minus 3 meter. That is to say a millimeter, a standard scale that you have. Probably you have one in front of you right now. I mean, with that scale, with that, the least count of that scale, you can't give me the measurement of 10 raised to minus 6 meter. That is to say a micrometer. So it's not that things are not happening on the micrometer scale, but you are not interested. Why are you not interested? Because your least count restricts your scale of interest in the physical universe. So scales of interaction forces are like that. So hereafter, be it understood, although we shall be talking about forces, as in electrostatic forces between two electrons, or in the case of this magnetism, we will be talking about Lorentz forces, stuff like that. But we shall not bring in things like mass into acceleration. So, because we are not really going to be interested too much in the mass of the electron. The mass of the electron makes a very small contribution to the forces of interaction, particularly on a scale where we are interested in electricity and magnetism. So that is the point. And there is this one last point I'd like to make today before I finish. I'm just nearing the end of that 5 minutes I asked of you. Under ordinary conditions, the net charge locally is almost 0. What do I mean by under ordinary conditions? Ordinary conditions as in the breaking of a copper wire or such something. The net charge locally is almost 0. But when you go down to the scale of the atom, it's not an ordinary condition. Going down to the scale of the atom is not a matter of ordinary experience for you, because nature has not designed you to think of the atom or even look at the atom. So that is an extraordinary condition where the net charge locally do not, I mean, the local, there is no local balance of charge. And I showed you the diagram in that separate set of slides. where I said that the central positive charge is separated from the electron cloud outside. And there is this one last question that I will not answer today. I don't have the time. In the next class, we shall take it up next Wednesday. Why doesn't an electron in an atom fall on the positive charge nucleus? You should be worrying about this question. If two charges attract each other, of opposite type charges attract each other, why is the electron going round and round? Why is the electron outside the nucleus? It should just fall. Attraction should cause it. And if electrostatic attraction on small scales is supposed to be so strong, stronger than gravity, 10 raised to 42, a proton and an electron will have mass, they will have gravitational attraction, fine. And since they are of opposite sign, they will have 10 raised to 42 times stronger attraction than gravity. They should be falling upon each other, but they do not. That question we shall take up in the next class. It's actually related to quantum mechanics. I'll just briefly touch upon it. I'm stopping the class now. If you have any questions to ask, you may do so. Otherwise, we may leave. You have any question, anybody? You can put in the chat. You should have put in the chat in case you had. Nobody has a question? So we will have these 45-minute class, 75-minute classes hereafter. In the last class, by mistake, I stopped earlier. I regret that error. So in the next two classes, I'll just take 5 extra minutes every day and cover up for this that shortfall. Thank you. You don't have any question, it seems. Then I request all of you to leave the class quickly, please, so that I can stop the recording.
Thank you, sir.
Thank you.